Welcome, ladies and gentlemen. We are going to be talking about impulse and momentum. Impulse and momentum deal primarily with things colliding or things separating. So this is a classic. It's called a Newton's cradle, where you have those balls, collisions. Those conserve momentum. Pool, something colliding, and then also something separating. So I've got a couple videos to just kind of start us off. Well, first, I think here's where I want to go. I'm going to go right into impulse and momentum, where it is derived. Impulse and momentum comes from this equation, F equals ma. And you know that acceleration is your change in velocity or your change in time. And then what you do is you take this change in time and you multiply it by both sides. So you end up getting F delta t equals m delta v. And we call this the impulse momentum theorem. Right here, we call this impulse. And an impulse is if you push or pull on something for a certain amount of time. I like to equate it to when you're a kid, how you go sledding and someone pushes on your back. The longer they push on you, the faster you're going to end up getting going. And this is, we call this momentum. Well, first of all, momentum is your mass times velocity. We use the Greek letter rho. It's like a P with like a curly thing. Momentum is your mass times your velocity. If you've got a lot of momentum, you've got a very large mass or you've got a very large velocity. It's the combination of the both. Now, this right here, this is a change in momentum because of that delta. And this is what this equation is saying, that if you push or pull on somebody for a certain amount of time, you're going to change their momentum. You're either going to slow them down or speed them up. And that's what this right here says. Impulse momentum. So there's a lot of really interesting applications of this where if you keep certain things constant, for instance, airbags work on this exact principle. Like you're in a car, right there. An airbag works to your car is going at a certain speed, like 55 miles an hour, and it goes, well, I'm sorry, take that back. You have a certain mass, and you're going from 55 down to 0. So this stays constant right here in that. But the thing that's damaging to people is how much force is on you. If we could somehow increase the amount of time that the force is acting, you don't need as much force. So this is a set number, like 100. So if you were to exert a time of maybe 20 seconds, over a course of like 20 seconds, maybe there's only 5 newtons of force. Or on the converse of that, if you only exerted it for 2 seconds, then you get 50 newtons of force. So the force and time are very important. The longer that you exert the force, the less force that you need to have the same change in momentum. We call this the impulse momentum theorem. And then there's an example in your book here. It's example problem 1. It says there's a 2,200 kilogram vehicle It's traveling at 26 meters per second. And you can stop it in 3 different ways. Way 1, you can stop it gently, where the time equals 21 seconds. Way 2, you can stop it not so gently, like slamming on the brakes, where your time is 3.8 seconds. Or you can run into a wall that stops you in 0.2 seconds. And the question is, what's the average force in each of these scenarios? So we're going to use the impulse momentum theorem. We have F delta T equals M delta V. My mass in delta V is going to be the same in every case. My mass, 26. My change in velocity, my final velocity, minus my initial velocity. It doesn't really much matter if you have a positive or negative. So 2200 is my mass. So I take 2200 and I multiply by 26. I get 57,200. Now that's going to be kilogram meter per seconds. Now, in each of these cases, the question was what's the average force? So what I'm going to do is put in 21 into here. So my force times 21 so I can figure out my force for the gentle. You take 57,200 divided by 21. I'm just going to store this as x so I don't have to keep coming back and typing it in. So I'll take x divided by 21 and I get 227.23 newtons. Now, for slamming on the brakes, we just change this number here, 3.8. So I'll take my number x again, divide by 3.8, 15,000. And then lastly, hitting a wall, 0.22. So I take my number, x, and I divide by 0.22. I like that, storing a number as x so I don't have to retype it in. It makes doing this a lot easier. 286,000. What was it again? 286,000. So you can see you have an incredible amount of force being exerted the faster you want to stop something. And you could figure out how much force is on the human body too. Instead of putting 2200 in there, you'd put your mass, like as a person, something probably around, I don't know, like 100 newtons, 100 kilograms is, I don't know what your average person is. But that's the impulse momentum theorem, that bigger force, less time if you have the same change in momentum.